You know, when we think about terraforming a planet, like making it perfectly suitable for modern life, we usually imagine a fleet of futuristic spaceships deploying these high-tech atmospheric
Right.
processors.
It's a very neat sort of science fiction solution to what is actually an incredibly messy, violent chemical problem.
Yeah, it's always clinical and engineered in the movies, but if you want to see how a planet actually gets terraformed, I mean, you don't need spaceships, you just need to look at the power grid.
Oh, absolutely.
Because the electricity running your life right now is very likely drawing power from this chaotic biological factory that Earth built over, what, 300 million years ago.
Give or take, yeah.
So welcome to this custom-tailored deep dive. We've got a really fascinating stack of research in front of us today, and our mission is to explore a time of just extreme biological weirdness.
It really is.
We are looking at giant, scaly trees, absolute monster-sized bugs, and the dramatic climate shifts that quite literally fueled the modern world.
I'd say it is arguably the most transformative period in Earth's history. We are talking about an era that fundamentally rewrote the rules of biology and atmospheric chemistry all at the exact same time.
Okay, let's unpack this. We are diving into the Carboniferous period. This spans from roughly 358.9 to 298.9 million years ago. And right off the bat, that name, Carboniferous, what does that actually tell us about what the planet was doing?
Well, the name kind of gives away the ending, in a sense. Carboniferous literally translates from Latin as coal-bearing.
Coal-bearing.
Yeah, and it is incredibly literal. The vast majority of the Earth's extractable coal deposits were laid down during this specific 60 million year window.
Wow.
And the period is really defined by two monumental innovations. First, you have the establishment of the first truly massive terrestrial forest. And second, the evolutionary explosion of four-limbed vertebrates, our distant ancestors, finally moving inland.
But before we talk about what was living on the land, we have to talk about the land itself, right? Because the continents weren't just sitting there in the shapes we know today. They were actively crashing together.
Oh, yeah. It was a violently active geological era. You essentially had two massive land masses slowly colliding. Laurussia in the north and Gondwana in the south.
Gondwana.
Right. This is the very beginning of the assembly of the supercontinent Pangaea. And, when continents collide, billions of tons of crust have nowhere to go but up.
Right, they just crumple.
Exactly. This slow-motion crash pushed up the central Pangaean Mountains. To picture the scale here, imagine a mountain range comparable to the Himalayas today, but stretching over 10,000 kilometers.
10,000.
Yeah, running all the way from what is now the Gulf of Mexico straight across to modern-day Europe and Turkey.
That is just a staggering physical barrier. I mean, it's hard to even wrap your head around. And because of where these continents were positioned right across the humid equator, it created this bizarre environment right at the foot of these new mountains, right?
Yes, exactly. The sheer weight of those mountains pushed down on the continental crust next to them, creating what geologists call foreland basins.
Foreland basins, okay.
These massive low-lying depressions that just filled with fresh water. And because they were sitting right on the equator, they became these endless, deeply humid peat mires and swamps.
And looking at our source notes here, those swamps were dominated by plants that would look entirely alien to us today. The biggest ones were these giant lycophytes, especially a tree called lepidodendron.
Lepidodendron.
But reading through the research, it says they didn't have wood like modern trees do. So how does a 10-story tree, like 30 meters high, even stand up without solid wood on the inside?
That is the truly bizarre part. We call them trees, but they were actually giant scale trees, distantly related to modern club mosses. A modern tree relies on its inner core, the xylem, for structural support.
Right, the wood holds it up.
Exactly. Lepidodendron was the complete opposite. It basically grew from its cortex, meaning its bark.
It's bark.
Yeah, the thick, scaly bark on the outside provided almost all the structural stability, while the inside was mostly just soft, pithy tissue.
So they were basically giant, rigid tubes of bark balancing in the mud?
Exactly that. And because they lacked deep, anchoring taproots, they relied instead on these shallow, sprawling root systems called stigmaria.
Oh.
So they were incredibly fragile. They would grow phenomenally fast in these waterlogged swamps, reach a massive height, and then a strong wind, or just a shift in the mud, would knock them over. They were constantly falling down.
Constant tree falls. So we have millions of massive 10-story tubes of bark falling down into these swamps. But they aren't rotting. They're just piling up layer after layer, creating the coal we use today.
Right.
Why weren't they rotting? What was missing from this ecosystem? Because I've seen this term delayed fungal evolution thrown around in the
Oh, wait,
research.
is the idea literally that these 30-meter trees were piling up like uncollected trash for millions of years just because fungi hadn't, learned how to eat wood yet? Well, it's one of the most fiercely debated hypotheses in paleobotany right now. The delayed fungal evolution theory suggests almost exactly that.
That's crazy.
Yeah, the structural compound that makes bark and wood so tough is a complex polymer called lignin. And the theory argues that plants invented lignin to grow tall, but there was this massive evolutionary lag.
Oh, I see.
It took millions of years for specific organisms, specifically basidiomycete fungi, which are the ancestors of many modern mushrooms, to evolve the specialized enzymes capable of breaking that lignin down.
So it really was just a planetary scale garbage strike. The trees fall, nothing has the biological tools to digest them, so they just sit there and eventually get buried.
That is the classic view.
Mhm.
And genetic analysis of modern fungi actually provides some support for this, suggesting those specific lignin-degrading enzymes didn't fully evolve until the Permian period, which came after the Carboniferous.
Okay, so case closed, right?
Well, no. It is actually a bit more complex than just a garbage strike.
Oh, really? How so?
Well, some geologists point out a massive flaw in that theory. We still had massive coal deposits form in the Mesozoic and Cenozoic eras, tens of millions of years after fungi had definitely figured out how to eat wood.
Oh, that's a great point. If the fungi learned to eat lignin, why did the Earth keep making coal?
Right, so the competing theory argues that it wasn't a biological failure at all. It was just geological perfection.
Geological perfection.
Yeah, you had continents sitting right on the equator, driving year-round, explosive plant growth. But crucially, you had that tectonic subsidence we mentioned earlier. The ground in those four-land basins next to the mountains was slowly sinking.
Oh, sinking under the weight.
Exactly. It was sinking at the exact same rate that the dead trees were piling up.
Oh, so it's a conveyor belt.
A perfectly balanced conveyor belt.
Mm-hmm.
The trees fall into the stagnant swamp water, and before any fungi or bacteria can even attempt to break them down, they are buried in anoxic, meaning oxygen-starved mud.
And without oxygen, they can't rot.
Exactly. Without oxygen, decomposition essentially halts. Whether the fungi had the right enzymes or not didn't really matter because the trees were drowning in mud way too fast to rot.
I love that. It's this perfect storm of mountain buildings, sinking crust, and hyperactive forests. But if we pull back, burying all that unrotted plant matter did a lot more than just give us fossil fuels, right? It hacked the entire planet's atmosphere.
It really did.
Because plants breathe in carbon dioxide and breathe out oxygen. If you bury the plant, what happens to the oxygen that was supposed to recombine with that carbon when the tree rotted?
The loop is broken, the carbon goes into the earth, and that free oxygen just stays in the atmosphere.
Wow.
And over millions of years, it builds up to astonishing levels. Well, estimates vary slightly depending on the geochemical modeling you look at. The general consensus is that atmospheric oxygen climbed from roughly 15% at the start of the period up to a staggering 25 to 30%.
30%.
Yeah. For context, today's atmosphere is only about 21% oxygen.
Here's where it gets really interesting. Because when you alter the baseline chemistry of the air that drastically, biology just goes wild. We always hear about giant bugs in this era. How exactly does more oxygen equal giant bugs? I mean, it's not like they just inhale more and magically inflate, right?
No. It comes down to the physical mechanics of how they actually breathe.
Yeah.
Insects and other arthropods don't have active bellows-like lungs like vertebrates do.
Okay.
They breathe through a network of tiny internal tubes called tracheae. These tubes rely heavily on the passive diffusion of oxygen from the outside air into their tissues.
Passive diffusion.
Right. So in a 21% oxygen atmosphere, there's a strict physical limit on how big a bug can get before the oxygen simply cannot diffuse deeply enough into its body to keep its cells alive.
So it's a bottleneck. The atmosphere literally suffocates them if they grow too large.
Exactly.
But if the oxygen jumps to 30%, it's like turning the whole environment into a pressurized hyperbaric chamber. So that passive diffusion is suddenly supercharged.
That is an excellent way to conceptualize it. That bottleneck is entirely removed, and the result is legendary gigantism. So it's like Mother Nature cranked the oxygen dial to 11, turning everyday garden pests into the cast of a monster movie.
Oh, totally.
You get creatures like Arthropleura. It is officially the largest known terrestrial invertebrate of all time.
I was looking at the reconstructed size of this thing in the source files. It's a millipede-like creature that grew to 8.5 feet long.
Huge.
Over 2.5 meters, just scuttling through the ferns. I mean, 8.5 feet.
Yeah, and the gigantism was literally everywhere. You look up and you have the griffin flies. The
Hmm.
most famous is Meganeura, which looked almost exactly like a modern dragonfly, but it had a wingspan of 30 inches.
30 inches. That is the size of a hawk.
It is. And on the forest floor, you had Pulmonoscorpius, an apex predator scorpion over 2 feet long.
I am just picturing a hawk-sized dragonfly swooping down through a misty swamp. It feels completely alien. But it wasn't just the land that got weird. The ocean had its own bizarre experiments going on, too. What was happening beneath the waves?
Well, the oceans were incredibly dynamic because of what happened right before the Carboniferous began. The end of the preceding Devonian period saw a mass extinction event that completely wiped out the dominant, heavily armored fish of the time, known as the placoderms.
So all the apex predators suddenly vanish?
Exactly. It left a massive ecological vacuum. And, nature abhors a vacuum. Without the placoderms dominating the food chain, cartilaginous fish, basically sharks and their relatives, underwent a massive evolutionary radiation. They expanded into all these newly opened niches.
And reading about some of these sharks, it sounds like evolution was just throwing ideas at the wall to see what stuck. There's Stephacanthus. The notes call it the brush fin shark.
Yes, Stephacanthus.
It had this flat, anvil-shaped dorsal fin with a patch of spiky denticles on top. Why on earth would a shark need a spiky anvil on its back?
It is incredibly strange, isn't it? The leading theory is that it was driven by sexual selection, possibly used in mating rituals or to intimidate rivals. Without the intense predatory pressure of the placoderms, these bizarre, highly specialized anatomical features had the breathing room to evolve and persist.
That makes sense. And then there's Adestus, which I can only describe as a nightmare.
Oh, yes.
It didn't have normal rows of teeth that shed like a modern great white. It had these terrifying, curved, buzzsaw-like tooth whorls right in the middle of its mouth.
Yes, the tooth whorls. As new teeth grew in, the old ones weren't shed. They were pushed outward, creating these massive projecting brackets of sharp teeth.
Just sticking out of its face.
Yeah. It completely changes how we think about how prehistoric predators captured and processed their prey. It was just an era of profound biological experimentation.
But this hyper-oxygenated, giant bug-filled swamp party couldn't last forever, because every action has an equal and opposite reaction. If pumping out oxygen was caused by burying millions of tons of carbon, what happens to a planet when you suck all the carbon out of the sky?
It freezes. You plunge the Earth into a deep, deep freeze. This is the late Paleozoic Ice Age. It was the most extensive and longest-lasting icehouse period of the entire Phanerozoic eon.
Wait, the Phanerozoic eon, just to ground us, what time frame are we actually talking about there?
The Phanerozoic is the current geological eon. It started about 538 million years ago with the Cambrian explosion of complex life, and it continues right up to today.
Okay.
So out of the last 500 million years of complex life on Earth, this Carboniferous deep freeze was the longest sustained ice age.
We're trying to piece this together. We always hear today about CO2 warming the planet by trapping heat, right? But here, it's the exact opposite. Did Earth basically sequester its own carbon so efficiently that it forced itself into an ice age? Like, could the forests alone really suck up enough carbon to freeze an entire planet? That seems like a massive leap.
If we connect this to the bigger picture, it wasn't just the forests. You were looking at the ultimate demonstration of Earth's climate feedback loops. The swamp forests were absolutely pulling massive amounts of CO2 out of the atmosphere and burying it, yes.
You're right.
But remember those 10,000-kilometer-long Central Pangean Mountains we talked about?
Right, the Himalayan scale mountains pushing up at the equator.
As those brand new mountains were exposed to the tropical elements, they underwent intense chemical weathering. Rainwater is naturally slightly acidic because it absorbs CO2 from the air.
Okay.
When that rain hits newly exposed silicate rocks in a mountain range, a chemical reaction occurs that literally binds the atmospheric carbon to the minerals. Those minerals then wash into the sea and lock the carbon away in layers of limestone and carbonate sediments on the ocean floor.
Oh, wow. So the plants are burying carbon in the swamps, and the mountains are chemically eating carbon out of the rain. They teamed up.
They absolutely teamed up, and the combined result was a catastrophic drop in atmospheric carbon dioxide. During the peak of this glacial period, CO2 levels plummeted to as low as 175 parts per million.
175.
Yeah, for context, pre-industrial levels in our modern era were around 280, and today we're well over 420.
So at 175 parts per million, the greenhouse blanket is practically gone. The heat just escapes into space.
Exactly. Global average temperatures plummeted. Massive, continent-spanning glaciers expanded across the entire south polar region of Gondwana.
And a glacier isn't just a static block of ice, right? It breathes. It waxes and wanes. The notes mention these were driven by Milankovitch cycles.
Yes, Milankovitch cycles.
Which are these subtle shifts in the Earth's orbit that happen over 100,000-year intervals. When the Earth's orbit brings it slightly closer to the sun, the ice melts. When it shifts away, the ice freezes. And every time that happens, global sea levels radically change.
It creates a planetary sea level seesaw. When the South Pole froze, the oceans shrank. When it melted, the oceans rapidly flooded the continents.
How do we actually see this in the rock record today? The source material mentions cyclothams, but what does a sea level seesaw actually look like when you stare at a cliff face?
It looks like a repeating barcode of ancient climate change. Walk through it chronologically with me.
Okay, right.
Imagine standing on a shallow continental shelf at the equator. The ice sheets at the South Pole grow, so sea levels fall worldwide. The land you are standing on is suddenly exposed. Rivers carve deep valleys into the mud.
Okay, so we have dry land and river valleys. That's the base layer.
Then the Milankovitch cycle shifts. The climate warms slightly, polar ice melts, and the sea level rapidly rises. The water backs up into those river valleys, turning them into massive stagnant swamps. Our peat mires?
Right.
Those swamps lay down a thick layer of plant matter, which becomes coal.
So that's layer 2, valley dirt, then coal.
As the sea continues to rise relentlessly, the swamp is drowned completely. It's replaced by a shallow, warm marine environment, which lays down a layer of calcium carbonate or limestone.
Okay, dirt, coal, limestone.
Finally, at maximum sea depth, the water becomes deep, still, and a noxic, settling fine silt that becomes dark marine shale.
Wow.
Then the cycle shifts again. The ice freezes, the sea falls, the shale is exposed to erosion, a swamp forms, the sea rises, limestone shale. Over and over and over again.
So you get these perfectly stacked, repeating layers, non-marine dirt, coal, limestone shale, dirt, coal, limestone shale. That is an incredible visual. But this extreme environmental whiplash, I mean, the seesawing sea levels and the plummeting global temperatures, that has to take a massive toll on biology.
Oh, absolutely.
The environment that birthed these giant scale trees is literally vanishing beneath them. What happens to a forest that suddenly finds itself in a freezing, rapidly changing world?
It collapses. This event is actually known as the Carboniferous rainforest collapse. The global climate snapped. It went from being hot and universally humid across the entire equatorial belt to being cool and highly arid.
The continuous, globe-spanning swamp forests simply couldn't survive without that constant moisture.
They couldn't. They shrank and fragmented into isolated islands of wetlands surrounded by harsh, dry, seasonal environments. The giant 30-meter lepidodendron scale trees that relied on waterlogged mud essentially died off.
They just couldn't hack it.
No, they were replaced by much less diverse, hardier flora like tree ferns, which could tolerate drier soils.
And if you're an animal that evolved to perfectly dominate a humid, waterlogged swamp, suddenly your entire universe is evaporating. What happens to the amphibians? Because at this point, they were the undisputed kings of the land, right? You had these massive crocodile-sized amphibians ruling the swamps.
They were the apex predators, for sure. But amphibians have a fatal physiological flaw when it comes to dry land. Their skin is highly permeable, meaning they lose internal moisture very quickly in dry air.
Right.
And crucially, their eggs are soft and jelly-like. They must lay their eggs in water, or the eggs simply desiccate and die.
So without water, an amphibian fundamentally cannot reproduce.
Exactly. So as the swamps fragmented and the air dried out, amphibian biodiversity suffered catastrophic, irrecoverable losses. They were trapped on shrinking islands of moisture, completely unable to cross the arid expanses between them.
It's like amphibians were stuck using landlines tied to the water while reptiles just invented the smartphone. The hard-shelled egg made them completely mobile and untethered from the swamps.
That is a perfect analogy.
Because while the amphibians were dying out, another group of animals figured out a way to cut the cord. I saw two specific groups mentioned in our source material, sauropsids and synapsids. What's the difference between them and how did they survive this dying, drying world?
Well, both of those groups fall under a larger umbrella called the amniotes. To clarify the terms, sauropsids are the evolutionary lineage that includes all modern reptiles and birds.
Okay, reptiles and birds.
Synapsids are a distinct, separate lineage that eventually gave rise to mammals, meaning us.
Oh, wow, okay.
The reason both of these groups survived while the amphibians perished comes down to one of the greatest physiological hacks in evolutionary history.
The amniotic egg.
Exactly. the hard-shelled or leathery amniotic egg.
It's basically a self-contained portable pond. It has its own water supply and nutrient yolk sealed inside a protective membrane.
Precisely. And combined with that, these early amniotes developed heavily keratinized scales on their skin.
Keratinized scales.
Right. Keratin is the same protein that makes up your hair and fingernails. On a reptile, it acts like a biological waterproof seal, locking their internal moisture inside their bodies so it doesn't evaporate into the dry air.
So they were completely untethered from the swamps. They had mobile eggs and waterproof skin.
The so what of this moment cannot be overstated. The collapse of the rainforests was a devastating tragedy for the amphibians. But it provided the exact evolutionary pressure and the exact empty ecological real estate needed to launch the amniotes.
Because they could handle the dry land.
Right, because they had the physiological tools to survive in arid, seasonal environments. They quickly expanded out of the dying swamps and conquered all these newly opened, dry niches.
The death of the swamps cleared the stage for the next massive act of life on Earth.
Those early amniotes, the creatures that survived the brutal Carboniferous rainforest collapse, are the direct, unbroken ancestors of every reptile, every bird, and every single mammal on Earth today.
Including you and me.
Including us. If the climate hadn't changed, if the forest hadn't buried all that carbon and frozen the planet, amphibians might still rule the world.
Okay, let's pull all of this together. We've traced an unbelievable chain reaction today. We went from continental plates crashing together to form a 10,000-kilometer mountain range, which created massive foreland basins.
Right.
Those basins filled with alien forests of fragile bark-growing trees. We explored how tectonic subsidence buried those trees, pumping so much oxygen into the air that millipedes grew to the size of alligators.
Huge millipedes.
And we saw how that exact same process, combined with the weathering of those new mountains, pulled so much carbon out of the sky that the Earth froze itself, triggering a sea level seesaw, destroying the rainforest and forcing our scaly ancestors to invent the hard-shelled egg just to survive.
It is a profound story of deep interconnectedness.
Yeah.
Biology actively changing the climate, and then the climate violently reshaping biology.
Yeah.
You simply cannot separate the geology of the Earth from the life that walks on it.
So what does this all mean? We started by talking about the energy grid. Over the course of the Carboniferous, the Earth spent 60 million years slowly pulling carbon out of the atmosphere, locking that solar energy underground, and fundamentally altering the trajectory of evolution to favor our ancestors.
Exactly.
Today, we are digging up those 60 million years of stored carbon and pumping it right back into the atmosphere in the span of just a couple of centuries.
And that's the kicker. The last time the atmosphere's chemistry shifted this dramatically, it wiped out the dominant life forms and handed the entire planet over to a completely new mutant branch of survivors.
Wow.
The question isn't whether life will survive our current carbon experiment. The question is, who or what is currently waiting in the wings for our climate to snap?
Something for you to think about next time you flip a light switch.